some of our recent research results at this lovely workshop. So my name is Robert Reeve. I'm from the group of Matthias Kloy in Mainz. And today I'm going to be talking to you about some of our recent research on using various magnetic imaging techniques to look at the current-driven dynamics of different topological spin structures, including magnetic skirmions and vortices. And at the outset, I'd just like to acknowledge the two main PhD students who've contributed to the two studies I'll be presenting, namely Pascal Krautscheit and Kai Litzius. So hopefully I don't need too much introduction for the present audience, just one slide of motivation. We're interested in these various spin structures because things like domain walls, vortices and skirmions, they can display quasi-particle-like properties, and that makes them useful for various device applications. Some examples include the famous data storage example of the racetrack memory based either on propagating domain walls through these nanowires or skirmions. Also, there's logic proposals similarly based on domain walls or skirmions. We've heard a bit about oscillators based on vortex states or skirmions in these pillars. And then also there are even commercially available sensors based on propagating domain walls in such nanowires. But in order to make such devices viable, there are a couple of ingredients we need. So firstly, we want to have spin structures that we can tailor and which are stable. And for the stability, things like the DMI come into play. And secondly, of course, we need to manipulate these states, and we want to understand the dynamics. So here is the outline of my talk. So that's it for the introduction. The main talk will now be in two parts. In the first part, I'll be talking about vortex state manipulation using currents, and in particular how through that we can determine some of the important dynamic parameters for the system, namely the non-adiabaticity beta and its relationship to the damping alpha. And then in the second part, I'll move on to magnetic skirmions and how we are able to move skirmions in racetracks, and then also some of our recent results on imaging the skirmion Hall effect. And then I'll finish up with some conclusions. So starting off on the vortex state systems, and for this work we are looking at spin transfer torque dynamics, and here we can describe such dynamics with an extended LLG equation. So we have the precession term at the start here. Secondly, we have this damping term based on this alpha, this Gilbert damping parameter. And then there are two terms due to the presence of the current, the adiabatic spin torque term and this non-adiabatic spin torque term characterized by beta. Now, in general, this value of alpha, it's Gilbert damping, it's relatively well understood, whereas the non-adiabaticity beta, it's less well understood. But you can, in general, have two contributions. One, a true non-adiabatic contribution, and that's related to the spin structure that you are looking at. So, for example, if you have a high gradient of the magnetization, then the electrons can't track that magnetization, leading to some non-adiabatic effects. And secondly, there's this spin relaxation contribution, which is related to the materials parameters of the system, and therefore you might expect it's also related to the damping. Furthermore, recently there was also suggestions that there might be a topological contribution to beta, because in general it's seen that for vortex states you do indeed see very large values of beta, which could be related to the high gradient of M at the vortex core, but you don't see quite such large values for narrow domain walls in PMA materials. Now, one problem with understanding all these beta in particular is that there are lots of different methods in the literature used to measure and lots of different spin states that are studied. So for example, even just for permalloy, the range of values goes quite a large span, and it's difficult to compare results based on different methods. But one approach which is relatively robust to measure beta is based on vortex state dynamics. And in particular, it has advantages based on certain techniques based on domain walls because it's not sensitive to edge roughness, which often pins domain walls and can lead to difficulties in interpreting some of the other results. So what we have is we start off with a vortex state, as shown here. We apply a charge current, and as we do that, the core will gyrate and eventually reach a new equilibrium position. And the direction in which it goes depends on these non-adiabatic and adiabatic components. So if we can use a technique to image this displacement, we can get the value of beta. Now, in addition to these components here, there's also potentially an Ørsted field contribution to this. And so in practice, what you can do is if you image different states with different chiralities and different polarities, by taking different contributions of these, you can extract just the non-adiabaticity component. And so here you have the equation. You need to have 3 different configurations. And here at the front, you just have some prefactor which you can get from micromagnetic simulations or analytical models. And then from this, you can extract a value of beta. So in our case, what we need is a high-resolution imaging technique in order to image this displacement. And we've used SEMPA, scanning electron microscopy with polarization analysis. So this is a lab-based technique that we have available. And being an electron microscopy technique, it has a very good spatial resolution of less than 20 nanometers. From the imaging, we simultaneously get 2 components of the magnetization and also an image of the topography. And by combining those, we can also get a full in-plane color map. So these are the samples that we've made. In this case, we have permalloy discs, 4 microns in diameter. And here you can see the contact pads. And firstly, what we want to do for these systems is analyze the damping. And this we do with ferromagnetic resonance. And through this, we can extract a relatively low value of the damping of 6.1 times 10 to the minus 3. Next, we want to image that displacement of the vortex core. So these are a couple of experimental images from the SEMPA. And you can see here, the black cross in the center is the center of the disk, the relaxed position of the vortex core. And as we apply these currents in these different directions, we're getting a different directional displacement of that core. And then we can repeat that for different current densities. And here you can see more clearly that for different current densities, we get a different displacement, but also crucially for these different circulations and different polarities of the state, we're getting different slopes and different directions of this displacement. And so what we do is we then take those slopes, and by using the slopes and not just these individual points, that helps to average out the effects of small pinning sites on that motion of the vortex core. If we go to too high current densities, then you sometimes find that this is no longer linear because of some anharmonicity in the potential. And in some samples, you might have strong pinning sites, in which case you also don't have a linear relationship, but you can extract those from the analysis. And in the case where you see this nice linear relationship, you can be confident that you're having robust behavior. So what we are in particular interested in is to see how this non-adiabaticity changes if we change the damping of the system. And for that, we move to a doped system where we can modify that damping. And we use dysprosium doping by co-deposition in ultra-high vacuum. So here you can see we use Rutherford backscattering spectroscopy to determine the composition of the films. We're getting around 2% or 1.7% dysprosium doping. And these are the line scans from the FMR. And you can clearly see that for the undoped system, you have a very low line width, whereas you're getting a much larger line width for the doped systems, consistent with a much higher damping. And you're getting a good agreement between these two cases of different batches of films with nominally the same damping. So if I move now to the values that we can extract from that analysis, firstly, for the case of the undoped system, we are able to get as I showed you before, this value of alpha, quite a low value of alpha. For beta, we're getting quite a high value, 6.7 times 10 to the minus 2. And that's consistent with these previous literature reports that for these vortex systems with a high gradient of magnetization, you get a large value of beta. We also get a large value for this ratio of beta to alpha. And this is important because, for example, domain wall velocities depend on this ratio. But if we now move to the doped system, here we see that we're getting a much larger value of beta, so 30 times 10 to the minus 2. But we're also getting a much larger value of this damping, and so within the errors at least, the value of beta to alpha is remaining rather unchanged. So overall, here we can see that indeed for this system, we have both this intrinsic or this non-adiabatic contribution due to the spin structure and also this materials parameters component from spin relaxation, which is scaling more or less with the damping of the system. So that's it for the first part of my talk. And now I'm going to move on to some of our work on magnetic skyrmions. So for this, instead of using SEMPO, we're using X-ray imaging. And the technique we use is scanning transmission X-ray microscopy that we perform at BESI and the ALS. For this, we have the electron bunches from the synchrotron, which you pass through an undulator to create your X-ray photons. These are then focused using a zone plate down onto our sample, and then you measure in transmission the transmitted X-ray photons. And then the contrast is provided via the X-ray magnetic circular dichorism mechanism. This is also a technique with a relatively favorable spatial resolution of around 20 nanometers, mainly determined by the zone plate. And as I'll show you a bit later, you can also do nice dynamic pump probe imaging. So for the skyrmions, we're in particular interested in seeing can we create some of these racetrack type devices. And so this is a schematic of one of the structures that we might look at. We have contacts where we can apply current pulses, and this is our material stack, which I'll introduce in a moment. And then in order to be transmissive for the X-rays, we fabricate the samples on these silicon nitride membranes. We then get characteristic black-white contrast, as you can see here, for the up-down magnetization within the samples. And the size of the skyrmions that we tend to have in our samples are between around 250 nanometers in diameter. So you can tune the size of that by applying an out-of-plane field, which helps to shrink the skyrmions down. The materials systems that we look at are these multi-layer stacks based on ferromagnets and heavy metals, where you have the interfacial DMI contribution. And here you can see an example of a wire where we've been able to start off with a number of skyrmions in the track. And then in this case, as opposed to spin transfer torques, we're using spin orbit torques to move the skyrmions. So as we heard earlier, one source of that is the spin Hall effect based on currents flowing in these heavy metals, which can then provide torques on the magnetization to move these skyrmions through the wires. And indeed, as we apply current pulses forward and back again, we can move these skyrmions through the tracks. But what we find is that actually the motion isn't always all that reliable. So while some skyrmions move very nicely, other skyrmions move with lower velocities, and even some are pinned and eventually annihilated. And so this is showing that you need to be very careful to, in particular, deal with pinning in these materials in order to have robust behavior of such a device. So what we then did was we moved on to a different material stack, in this case based on cobalt iron boron, which is an amorphous material with low pinning. And here now you can see, again in these quasi-static imaging, that we're getting not perfect, but certainly much more robust back and forth motion of these skyrmions. And indeed, if you extract velocities from these systems, we're getting some very nice skyrmion velocities of greater than 100 meters per second. Furthermore, if you look at the strength of the torques in the system, we're finding that the torques are very efficiently moving those skirmions through the nanowires. But one thing in particular that we are interested in is the skirmion Hall effect. Because for these topological spin structures, you expect not only displacement of the skirmions in the direction of the current, but also you have a Magnus force on these skirmions, and so you expect some transverse velocity to the skirmion motion. And to investigate this, we carried out dynamic imaging of these systems. But in order to get enough contrast to do such imaging, we need to have pump probe imaging, where we integrate over a very large number of repetitions of this process. And so for this, we use these bipolar pulses, like here. So we firstly move the skirmions forward, and then move them back again, and repeat that process many times, so that we can get enough statistics for getting nice contrast. But one consequence of that is that if we then do see contrast in our final images, we know that it must be related to the motion that is very reproducible, because otherwise the contrast is just washed out in the final images. So if we then look at imaging these skirmions during the pulses, as you can see by these black points here, we're getting a very nice agreement between the motion of the skirmions and that current path that we're applying. So it's showing that we're getting in-phase motion of these skirmions with the drive, and that points to having a low inertia of the system and a low mass of these systems. But next we, of course, are interested in this skirmion Hall effect. So now I can show you some movies of that now dynamic imaging during those pulses. So here we have our wire, it's at an angle along here, and you can see by this arrow here the direction that the current's flowing back and forth. And indeed, you can see that the skirmions are now moving along an angle with respect to that current. So we are indeed seeing this skirmion Hall effect. But one other thing that you might notice, so here we have imaging for this current density, 3.5 times 10 to the 11. If we go to a slightly higher current density, as shown here, then we're getting a much larger angle for this skirmion Hall angle. And so this is showing us that as well as having a skirmion Hall angle in the systems, we are also seeing some drive dependence of this skirmion velocity. And this fact, is something that I want to look into a bit more detail. So if you take simple models or simple simulations, for example, you can do some modeling based on the Taylor equation. And if you just assume perfect systems with no pinning and no internal excitations of those skirmions, then you expect to have a independent, velocity-independent skirmion Hall angle. So you can extract this expression, and it's based on the topological charge. So for opposite topological charge, you get opposite motion, and the damping of the system and this dissipation tensor, which depends on materials parameters of the system and the size of the skirmions. But if you put into the values for our systems, you get a value of around 60 degrees, which you can see is much larger than the values that we're seeing here. But of course, we don't have a perfect system. Real systems, as we've already seen, can be very prone to things like pinning, and potentially also to internal motion and internal dynamics of the skirmions. And there's also been some theory work looking at the effect of disorder on the skirmion motion. So for example, for these particle-like simulations, in this these publications here, it was shown that indeed, if you have disorder, then that can strongly suppress the skirmion Hall angle, because as the skirmion starts to move at an angle with respect to the current, it then gets pulled back towards the pinning sites, and it has preferential pinning on one side of the defects, and that reduces the size of the skirmion Hall angle in the creep regime. Eventually, though, if you get to the flow regime, according to these simulations, they see a saturation at roughly this value, depending on the material's parameters. Now, there have also been some measurements of this by the group of Axel Hoffman, and there they have quite large skirmions. They're able to see them using their microscopy. And in their case, they indeed saw some different regimes in the skirmion Hall effect. At low current densities, the skirmions were pinned. Then in the creep regime, they saw this linear increase in the skirmion Hall angle and eventually a saturation. But in our case, we're seeing also this change in the skirmion Hall angle with the velocity of the skirmions in the flow regime. And this made us think that there must also be some intrinsic contributions that are, in addition to this pinning, playing a role. And there are a couple of things that we looked at. We looked at whether, for example, variations in materials parameters could also account for this, but in our simulations, they only accounted for about 5-degree fluctuations. And there are a couple of ingredients that we took into account for our modeling. The first ingredient is the fact that in addition to the damping-like torque, you can also have quite a sizable field-like torque in these systems, and that can also affect the motion of these skirmions. So if you take that into account in these simulations, you can see that if you have no field-like torque, then there's essentially no drive dependence, but as you change the ratio between the field-like and the damping-like torque, you can get very different trajectories. And then secondly, a key ingredient in this is the fact that the skirmions can deform during the motion. So we can see in our simulations that we also get deformation, and that also means that as we increase that deformation with increasing drive as a result of this field-like torque, then we're getting increasing skirmion Hall angles. And there are also, based on analytical models that take this into account, you see that indeed you need to have this skirmion deformation in order for this field-like torque to be acting. Now, so far we have seen these few different regimes of behavior in different experiments, but the question is, can we now try and unify this into one picture and see these different regimes in one single case? And so I'll now go into some of our more recent results, just to finish off, where we've looked at some of the temperature dependence of this skirmion Hall angle. So in this case, we have a slightly different material stack, but it's still very similar to the ones we have before. And we look at the trajectories via quasi-static imaging at different temperatures. We need to take into account, of course, the heating of the sample due to the current pulses that we apply. So we can correct the cryostat temperature for the extra Joule heating. And if we then group those temperatures into different temperature bands, we can see that as a function of current density, we get these behavior of the velocity of the skirmions. So firstly, you can see that there are different threshold depinning current densities, reminiscent of thermal activation. And then after that, you have this linear increase as seen here. Now, in the first case, we were quite surprised by the fact that we saw quite this large difference in the temperature dependence for these different cases in the flow regime up here. But then we remembered that, of course, the current density that we apply isn't the whole story for determining the torques on the skirmions, because the spin Hall angles and the resulting torques are also strongly dependent on the temperature. And so we did some second harmonic measurements to measure the size of those torques as a function of temperature. And if you then renormalize these curves, then we get a more uniform, universal behavior for these different cases. So finally, how does this affect the skirmion Hall angle? So this is my last slide. So what we now see is if we plot these skirmion Hall angles as a function of the velocity of the skirmions, we now see different regimes of behavior. So at low velocities in the creep regime, we see this change in the skirmion Hall angle with the velocity as predicted. But then, as we go into the flow regime, we also see a change in the Hall angle with velocity, but with a different slope. And this, again, if we do micromagnetic simulations, taking into account the pinning structure within our materials, we can see that in this regime we're also getting this deformation of the skirmions. And so we think here that we're getting both, in the creep regime we have this importance of pinning on the structures, but eventually in the flow regime we get to a case where this deformation of the skirmions is important and these field-like torques are playing a role. Maybe also there's another slope up here, but there's not much data at the moment to really say one way or another. Okay, so with that I come to my conclusions. So I've shown you that we can use different imaging techniques to image various topological spin structures. In the first part I showed you that you can change the alpha and beta parameters by dysprosium doping, and that in these vortex type systems you have both non-adiabatic and spin relaxation contributions to beta. And then I showed you in the skirmion racetracks that you need to be very careful in controlling the material's properties, but that you can then image the skirmion Hall effect, and that there are different regimes of behavior, including pinning, creep regime, where pinning is also important, and finally deformation regime. So I'd like to finish off by acknowledging the various other authors from around the world who have contributed to these different projects. I also like to acknowledge the various funding bodies who have made all this work possible. Here's some recent publications on related topics, and I thank you for your attention.